Hello, welcome everybody. So the plan for today is to speak about atomic congestion games when you have stochastic demand. This is joint work with Roberto Cominetti, Marc Scarsini, Marc Schröder from Chile, Italy, and Germany, respectively, and myself. So this has been a traditional topic for a conference like this. So I think this is the 20th anniversary this year that people have been looking at these problems in this community, in the EC community. And kind of the main problem is that we all face traffic, both in traffic network, like in cars, like urban traffic networks, but also telecommunication networks, supply chain networks. There are all these many settings where we face congestion, and the decision makers are, in general, in this case, the cars, and they behave as equilibrium. And what people have been studying is what are ways in which equilibria differ from a centralized solution that can be as good as possible. And people look at, this duality between the two, look at the worst case gap, and that has been called the price of anarchy. And people have explored, for different models of this kind, what's the difference between these two objects. So traditionally, many of these games were defined in a deterministic setting. And in the last 10 years or so, more and more people have been looking at cases in which things are stochastic. So what we propose in this paper is to look at a very simplistic way of looking at stochastics of players. This can be looked from the perspective of supply or demand. In this case, we're thinking about players that are stochastic. In particular, a very simple way of being stochastic, which is when we plan for traveling, we think that there are going to be so many people out there in the road, and it may turn out that some people end up not traveling. Not traveling means that maybe they cancel a trip and they end up not going to where they thought they were going to go, or maybe they end up traveling at a different time of the day, and therefore they are not going to be interacting with you out there in the road. So the question is what happens in that case? So how good or bad the equilibrium turns out to be when players are stochastic. So this is a summary of what we plan to do. So it's a preview. So, and this idea of parameterizing the price of anarchy by some parameter that describes the network has been also used significantly over different work. What we plan to do here is to parameterize that by the probability. And let's assume for now there is a single probability that people are or aren't going to be present in the network. And let's parameterize that price of anarchy over that probability. So we know, and this has been proven in the past, that for atomic games, if people are present with probability 1, the price of anarchy is 5/2. That's the celebrated result. We know that's tight. We have upper bounds and lower bounds that match. We also know that for non-atomic games, the price of anarchy for affine congestion games like this is 4/3. That's a result by Raphael and Tardos in 2002. So the question is what happens in the middle? Well, not in the middle. So there's something else to say also. So as you reduce the probability, one of the questions is the atomic game going to be behaving like a non-atomic game? And this is one of the things that we try to investigate in this work. So the preview is the following. So if you look at that graph that I presented up there, and you look at the red line which corresponds to the price of anarchy, what you see is that you have a non-decreasing function that goes from 0 to 1 for the probability, and it goes from 5/2 for 1, which is what I said earlier, and as p, the probability that you're present in the network, gets to 0, then you converge to 4/3. There are a few things that are surprising there. We didn't expect this, but this is what happens after you do all the calculations, which is for any p which is closer than 1/4, then that line is flat. So we expect this to be non-decreasing as it is, but we expect that to get to 4/3 in the limit, not the way this is going. And we don't have a great explanation about this is happening, but this is what comes out of the calculations. We're still working to try to understand why it's flat there. So mathematically, I can show you it's flat. There's no problem. But the intuition of why it's flat that way, we don't quite understand yet. Then looking at the price of stability, which is a different metric that has been studied a lot, then it's also monotone decreasing, or increasing, sorry, but with a different rate. And all those things are tight, and this is what I plan to speak about in this talk. So let's backtrack, and this is just to give a full description. A congestion game, or we can think of a routing game, is a game in which you have resources, and you can think of resources to be arcs in a network that get congested, and therefore there is a cost function that will map how many people are there to how long each of these people are going to be in the network if you select that resource. There are a set of types that you can think of OD pairs in the network game setting, which describe the demand. And for each of these types, we have a set of strategies, which are if you think of the network game, that's going to be a set of paths that are described between an origin and destination. And it can be arbitrary for a general congestion game. And finally, there is a demand function. A demand is going to be how many players are going to be of each type. So that's a simple example. So we have two OD pairs, so O1 and O2. Sorry, one OD pair is O1 to D, the second OD pair is O2 to D, and then the graph describes all the possible paths there. So people who study this describe these games in different ways. So you have a non-atomic version of this where all the demand is divisible. You have the atomic case in which the demand cannot be divided, so it's controlled by a single player. But then the question is whether that single player can take different strategies and split the flow, or they can take only a single strategy to route all the flow. So those are the first lines that I have there: non-atomic, atomic splittable, and atomic non-splittable. And then what we're going to analyze is the case of stochastic players, in which players can or cannot be present in the network. All right, so now, as I said, in this particular setting of this game, a given player is going to show up with probability pi. So I don't want to focus too much on the notation, so I highlighted what you guys need to know. This is the most important, and I won't focus too much on that. So pi is the probability that somebody is present. Now, if you look at all the players on a given arc, and you sum that up, I'm going to denote by n. That's going to be the random variable that describes how many people will show up in that arc. And then an indicator variable y, i, is going to be whether a given player I is present on an arc E, right? And that's stochastic. It's going to depend on whether the person actually travels or is ended up not traveling. So with this setting, I can define what's an equilibrium of this stochastic game. And basically, we're going to assume that people are risk neutral, so people are going to take expectations. So if I decide to travel, I know I'm going to be there in the roads that I selected to travel. So I pre-selected path. This is a static game. So I selected path. I know where I'm going to be. What I don't know is what the others are going to be doing, but I can compute an expectation of that. And an equilibrium is an assignment where the path I'm taking in expectation is going to be lowest compared to any other path I can be taking, where I'm randomizing over what the others end up doing, but I know I'm going to be there. Okay? So that's the definition of equilibria. What I want to know is how good those equilibria are compared to the best I can do if I'm a central planner. So as I said, this has been looked by different people in the deterministic setting but for the last 20 years. For the stochastic setting, maybe less so, but still there are several papers that look at related problems like this. So in particular, what I want to call out is all these satisfy the smoothness framework that Ralph Gardner came up with a couple of years ago. So if you look at that, you can already get bounds on this game. But the bound you get is 5/2. So that framework directly, if you apply the results of that paper in 2015, doesn't give you anything parameterized by P. So what we do in this paper is to look at that framework and then adjust it. So when you fix P, then you can compute your bound for the price of anarchy. By the way, another thing to note is that so Clear and Schaffer, they have a paper in which they model user perception. So people perceive travel time differently. And if you use the model correctly, it can give you a result for our model as well. And we make that connection in some of the slides later. So this is something I mentioned earlier. So I'll go fast here. So the price of anarchy is going to be between so it's going to be below 5/2. What we want to do is we want to parameterize that over P. Okay, so to make things a little simpler to start, let me assume that all the PIs are equal to a given number P. So players are going to be present with probability P regardless of who the player is. Then you can extend that result to different PIs if you want to. So the first thing to note is that this game, which is stochastic, can be mapped to a deterministic game, where you need to replace the cost function by the expectation of the cost function when you assume you are there and the other players are going to be there with a binomial distribution for k-1, which is the rest of the players, and probability p, which is the probability that each of these players is present. So this can be analyzed analytically. If you replace one cost function by the other, then your game is now, this Bayesian equilibrium of the stochastic game gets transformed into an equilibrium, a normal equilibrium of the deterministic game. And you can solve that, which is what we do. Good. So now talking about social optimum, we need to also describe what's the social welfare in the system. So you can compute the total cost in the system by looking at the expectation of the cost. So you have a P in front of the expression on top, because if the person doesn't travel, then the cost is 0. Nothing is realized because the person is not there in the network. But if the person travels, you have to multiply the length, so the total cost of the path that the person selected by, so along the path where the person is. And that's the expression on top. And if you sum that over all players, what you get is basically the total cost in the system, which is basically for each of the resources, you have to sum the cost of that resource in expectation times how many people are going to be there, and then take the expected value of all that. So that defines also what the cost function is, and now you can define price of anarchy as the ratio between these things. So price of anarchy is the supremum over all instances of the worst case ratio when you take the worst equilibria, and the price of stability is the same concept when you take the best equilibria. So that's all standard definitions, but here we have expectations because it's a stochastic game. Now, one thing to note is that when you restrict this to the affine case, so where cost as affine functions of the form A plus BX, then you can evaluate all this. So the expectation of a binomial, you can evaluate very easily, and then you can just write this expression. And if you start with an affine function, then after you transform this cost into the corresponding deterministic game, you still get an affine function. But one thing that if you start with a linear function with no constant term, then things will get mixed and you'll get all the terms of the polynomial. So if you start, for example, with a BPR function of degree 4 plus a constant, then you get all the terms, all the moments of these binomials, and that complicates the analysis. But for the purpose of this paper, we only took affine costs, so things are easy enough. So quick example, if you have a network like that, the one like I showed before, then if both players take the direct arc to the destination, then the expected cost is going to be 1 and 1. That's obvious. If they take the indirect arc, in which you go to the other node and then to the right, then you get 2 and 2. But if both of them take one direct, the other indirect, then both will mix in the arc that goes from the left to the right. And then the expectation is going to be 1 plus P, which is the probability that the other is there. That's the expected cost coming from the other player being present in that arc. So looking at Smoothness Framework, what Tim Raphael improved, and this was based on many results in the past, in particular Harks and Begg, but also other papers that use variation inequality in the past. What these results come from is by looking at a deviation from equilibrium from a player and mapping that to the cost of the two strategies, the equilibrium strategy and the socially optimal strategy, and looking at these two constants, lambda, mu, and then operating by that. So what Tim Raphael improved is that if you can guarantee that smoothness condition, then the price of anarchy is equal to lambda over 1 minus mu. So that's one known. And what people have done, knowing this, is to try to come up with conditions that guarantee smoothness, and then optimize over lambda mu to try to get the best bound for the price of anarchy. So following that path, what we did is actually to characterize smoothness. So we have this inequality, which needs to be valid for all k and m. So that's kind of a complex inequality, but it's just algebra. So you write that inequality, try to optimize over k and m, and do the best you can there to optimize lambda and mu. So the first lemma is that if that inequality is true, then you have smoothness, and therefore you have a result on the price of anarchy. So what remains to be done then is optimize over lambda and mu. So there you define the optimization problem. So you have to come up with the best lambda and mu that will give you smoothness. And the first thing we noted when we did that is that actually instead of having these two parameters that we need to optimize on, lambda you can reduce and therefore kind of get rid of. So if you write lambda that way, that reduces into a single parameter optimization problem. So in doing that, basically you transform that optimization problem into a min-max type of problem. So what you do is after you transform it, so you take away lambda, you rewrite it so it depends only on mu. So now you have a single dimensional optimization problem that depends on mu, and then you try to find that optimal solution. So in doing that, because of this min-max, what you end up doing is you end up writing this as a function of y, where y is a transformation of mu to make it linear. So then you have this upper envelope on this y, and you're going to take the maximum, where all these lines are different realizations of k and m. So this upper envelope is what you're trying to minimize. That's the min-max. And then you take the best vertex you can. And that's going to be the minimum of this, which is going to give you the price of anarchy for a given p. Notice that as I change p, all these functions are going to be changing. So what you're trying to do is you're going to try to solve this parametrically for all different p's. And then that's going to give you the curve I showed you at the beginning. So that's the whole plan. Right, so we find p, for each p we find y, and for y we go back to lambda mu, which is what's going to give you the price of anarchy. So the way to do that then, so you try to work with all these facets of this upper envelope to try to see what's tight and what's not tight. And because the solution is going to be on a vertex, you need to guess what are the tight vertices. And by doing that, you get these thresholds. And you see that at the end, this optimal solution happens in three different regimes. So for the low p, you have this flat portion I showed you at the beginning. Then you have a concave part, which is the one in the middle. And then you have a convex one, which is the upper one. And by doing the algebra and showing that that's actually the optimal solution, you can get to these optimal lambdas and mu's. And from the optimal lambdas and mu's, you can compute actually the price of anarchy, which is what I showed you earlier at the beginning. So that's an upper bound for each of the three regimes of the 0-1 space. And then from there, obviously, you like to know that that's tight. So again, going back to the optimization problem, you can look at the dual variables of these tight facets. And from there, you can try to work a little to guess how the good lower bound looks like. And after trial and error, we came up with like these three instances that, by the way, are affine. They don't use any constant costs here, only linear costs. So this is, for large p, for medium p, and for small p, you get things that are matching the upper bounds I showed you earlier. So in summary, what you get is price of anarchy is tight with that curve I gave you earlier. And then if you want to look at price of stability, you can use a clear and Schaffers bounds for the upper part. This is what they prove in the paper if you interpret the results in the right way, so they work for us. And then the results we have for the lower part, because we have a tight bound for the price of anarchy and stability, so for the price of anarchy, and there is a single equilibrium, then you also get a bound for the price of stability. And then that completes the picture. All right, so to finish, let me conclude right on time. And so we talk about tight bounds for the price of anarchy and stability for this case of stochastic atomic congestion games and affine costs. I didn't get time to talk about different P's, but basically things are monotone. So everything will end up working out if instead of using if you have different PIs, you take the maximum of the PIs, then things work fine and all these bounds are tight and they work fine. I think what's more interesting is how to extend this. There are several open questions. One is to look at general costs. We only look at affine, and this is not general enough. Actually, in transportation, people like to use these quartic cost functions, and we are not yet there. So even for quadratic, we don't know whether things work, but we think that, yeah, some of these things will extend. Another interesting thing is about convergence. So when p goes to 0 and n goes to infinity, if n times p is constant, then you have a Poisson type of distribution, and you can try to characterize things that way. And then, last comment. One thing we assume is that people make decisions before the realization of the uncertainty. One thing that is interesting to look forward is what happens when people get some signals of the realization of uncertainty before making a decision of what path they're going to be taking to go to destination. Let me conclude here. Thank you very much.